Really am delighted to be here today. And so, yeah, so today the title of my talk is Reinforcement Learning for Realistic Movement. And so I've been working on animation for a long time. However, recently most of the work in my group has actually shifted towards working on reinforcement learning based methods. And so instead of going into the low-level details of reinforcement learning and a variety of methods, the arc of this talk will stay at a fairly high level, and so I hope that that way the broadest possible audience can get something out of this talk. So let's. Sorry, let me just move on here. Okay, so here's my brief cartoon history of character animation. And so over the past 40 or 50 years, so things began with keyframing, where you have direct artist control over every piece of the motion. Then we moved into a phase where with the advent of motion capture data, now we could develop many more data-driven methods driven by that data. And then, but also in parallel with data-driven methods, we've seen a lot of work on physics-based methods. And so this applies both to things like facial animation and fluids, but it also applies to full body character motion, which is basically the subject of my talk and my particular interests. And so yeah, with the introduction of full body character simulation, then the control you needed to make those characters walk and do other things was typically consisted of kind of handcrafted control methods. Now, so all of these, as we've developed data-driven methods and physics-based methods, artist-driven control still remains important. And so while I've presented them in this particular order of artist, data, and then physics, that doesn't mean that they don't overlap and that all of these are not important. And so in the end, really we want the best of all worlds. And so so in practice, what we do is we combine. We might include artist-driven objectives, artist-driven input into the objectives. Then we want to combine that with the benefit of motion capture, and then we want to maybe combine that with the benefit of physics. Use some algorithm to combine all those three components of the motion of what we want, of the motion specification, and then we want to create a motion. And so so we want motions to be both directable and natural. And so now the interesting thing about this kind of formula, if you want, is that this is also very much what reinforcement learning is about. So in reinforcement learning, we don't necessarily have the motion capture data, but we have the objectives and we have the physics, and then we have an algorithm. And so typically a reinforcement learning algorithm that produces a controller and then a motion. And so the question is, are we now able to move into kind of a new phase, or at least for physics-based full body animation, where deep reinforcement learning can really do many new things and opens the door to new possibilities. So this is kind of the overall theme of this talk. What's both the good and the bad of deep reinforcement learning? So let me sketch this out by I'll sketch out the hype curve for any phenomena, and so including reinforcement learning for animation or anything else. So basically, at some point, we have a technology trigger, and people get really excited about using a particular method. Then let's say you get really excited about using reinforcement learning for, you see the potential of it, and you get really excited about using it. And then when you actually start trying to implement it for the problems that you want to solve, then you might find that it's really tough to get it to do to get it to solve the actual problems that you want. So you have the kind of trough of disillusionment where it's not nearly as good as you thought it was, and it's much harder to get it to work than you thought. And then over time, as you begin to understand the method and what it can do and cannot do, then and we make improvements to the method, then we have the slope of enlightenment, and then eventually, we get to a stage where we can actually really begin to use these tools. So the arc for this talk will more or less follow this this kind of arc where I'm going to portray reinforcement learning as being absolutely fantastic. Then I'll describe some of the problems and limitations, and then I'll describe over the past 5 years how we've continued to make progress on the slope of enlightenment, and hopefully getting to this plateau of productivity. So let me pitch you the advantages of reinforcement learning. So here's an overall picture. So in principle, it's a really nice framework for creating motion. So in principle, all we need to do is specify rewards, which somehow describe what kinds of motions we would like, and the properties they should have. And then through trial and error learning with physics, we can, in principle, learn what's called a policy. And so this policy, for example, will produce the joint torques of a walking character, and then those joint torques or actions can drive the physics-based simulation. And then as the simulation advances, it produces rewards. And so it might be penalized for falling, or it might be rewarded for making forward progress. And it might be penalized for using large joint torques. And those can all be mixed into the rewards. And then as the simulation advances, it's important that the policy understands where the character is, or what the character state is, so that it can respond and adapt. If it was pushed forward, it might want to take a larger step forward, etc. So this policy will be represented by a neural network. And it's parameterized by a set of parameters theta, which is typically a neural network. And then the job of reinforcement learning is to set and train these parameters theta, so that you now have this magical black box, which can possibly look at the environment. So it could look at what the local terrain is, and it can look at what the character state is. And this magical black box, it's a little bit, ideally it does what you do when you walk up and down hills and do a sport. It takes your current situation and the context into account, and then it figures out, and then you figure out based upon that what action you should take. And most reinforcement learning algorithms, they need to do some exploration. And so typically in most model-free reinforcement learning algorithms, this is actually done by adding some Gaussian noise to the action space. And so even a fully trained policy will typically, in training, always be adding a little bit of Gaussian noise to its actions. And so this is also what makes reinforcement learned policies robust, because in practice, it's a bit like if you're driving a car, for example, it's a bit like there's always someone pulling on your steering wheel a little bit, adding some noise, so that you're always forced to learn a policy which takes you back to where you want to be. So keep that in mind when you're seeing these reinforcement learning results. A lot of the robustness effectively comes from self-perturbation during the learning process. Okay, but so this is magical, in some sense. You specify rewards, and then through a trial and error learning process, with typically millions or tens of millions of simulation steps, we learn a policy which can do really nice things. And so you'll see plenty of examples of that. But let me, and so this seems really promising, and a very general method. So these are some results from 5 years ago, but started out with methods that could play all Atari games, and then and then these OpenAI Gym results start to look a lot more like the problems that we actually want to control. And so, by the way, a lot of these actually originally come from the animation literature. Or from folks who also worked in animation, like Sergey Levine. And and then also could be inspired by robotics. And of course, more recently, AlphaGo, AlphaFold, and then Dota 2, and OpenAI solving Rubik's Cube with a robot hand, and much more. So the question is, what does this mean for animation? And so, well, again, let's look at where we were, maybe 4 or 5 years ago. And so, this is where, as people who work on animation, despite the very promising nature of these results, when you look at these motions, you don't particularly think that animation is solved, is truly solved by reinforcement learning. So don't get me wrong; these are fantastic people doing fantastic work, but the objectives for those really focused on reinforcement learning and machine learning are slightly different than those of us working in animation. So that's one challenge. Another challenge is the details of getting it to work, right? And so a lot of the early work and work in reinforcement learning continues to be done on certain benchmark problems, where in the benchmark problem, you don't have to worry about setting the simulation time step, designing the reward, designing the state description, determining what state description you need, determining So there's many decisions you need to make to work with the deep reinforcement learning. So I'm just sketching out some of these. Some of these are related to the environment, so the structure of your character, the torque limits, the friction, and then many are related to our details related to the algorithm. Okay, so what initial state should your character start for each episode? How much noise should you be adding to the actions? What's your batch size? What step size should you be? Step size control should you be applying to your policy updates? Things like early termination, and plenty of details that you need to get into. You need to resign your reward function. You do need to worry about local minima. So if you're getting poor motion quality, how does that, how do you fix that? And if it takes hours to run your algorithm, then how do you debug that in that setting? So many challenges here. And a last challenge is that of reproducibility. This isn't so much reproducibility for any single results where people will provide the code, et cetera, but it's really reproducibility to show that some new version of reinforcement learning is actually truly better than the old version, than previous versions of reinforcement learning algorithms. And so the incentives are such that you're always you always need to do better than the current state of the art. And so the standards and for reproducibility of the performance improvement over previous versions, over all possible previous reinforcement learning algorithms, are maybe not where we want to be. And so this was this paper that I'm showing here from 2017, I think. Talked a lot about that and how we need to do better for evaluation, et cetera. Okay, so given those challenges, now we're in the trough of despair, in that using reinforcement learning, it doesn't necessarily produce realistic motions out of the box, and there's a lot of parameters to set, hyperparameters to set, et cetera. So now let me try to build you up again to convince ourselves that we can do really interesting things. So in what follows, I'll be presenting, largely, I'll be kind of emphasizing a work work from our group, because that's what I'm really most familiar with. But I'll also be presenting work from other groups and painting some more general trends. So here's some work from basically 3 or 4 years ago that first really tried to show how we could combine motion capture and reinforcement learning in the simplest possible way. And so simple is good, and can be highly effective. And so we should explore simple before we try to use more complex methods. So here we're going to introduce motion capture. We're going to push it into the objective function. And so the simplest way to do that is to have some kind of a some kind of perhaps an L2 difference between at any point in time. You see where you are in your simulated motion, and then you know where you should be in some kind of a reference motion motion capture clip, and so maybe a walk cycle, and then we come up with an error metric that says how far are you away from the desired pose that you want it to be in. So that's going to be part of an imitation objective here with some weight in front, omega I. And then there's also another weight for a goal-related objective. And so, for example, in a kicking task, maybe your goal is to imitate a reference kick, but now you want to imitate that with physics, and you want to also hit this target. And so we're going to simply add this in with this goal or task objective. We're going to design a separate reward for that, and we'll combine this in an additive fashion. This kind of additive fashion isn't necessarily always absolutely the best way to combine those, but at the time we wanted to show that you can actually do interesting things with that. So this is so already this was just a very early test of this it really just contained a single motion capture clip of a lower body just walking forward, and then I think we also had some data from shallow turns, and so this is trying to imitate those objectives. That's part one of the objective, and a second objective is basically it's trying to it's also trying to hit these next two footstep locations. And so you can steer this thing by this. So the task here, its task is to hit these is to hit the next footstep location, and it's also given access to the footstep location that's 2 steps into the future, so that it knows if it needs to prepare to turn or prepare to go straight, etc. So this is already really nice. We're getting some really natural looking walking, and indeed we can put this into interesting environments where it's responding and trying to maintain its balance as it walks over these moving conveyor belts. And so yeah, we're really starting to get some interesting behaviors. We can stylize this. So here we can change the objective target to here walking with a straight leg. We're restricting the physics to have 1 or 2 straight legs. And yeah, so the nice thing is, you as an animator, you can just come up with these constraints. You can add it to the system and retrain a new controller, so you can get a variety of interesting motions. So I'm not going to dwell too much longer on this. A basic question is, okay, does this extend to more complex motions? And so this is what we did in the 2018 Deep Mimic paper, where now we're going to have a state description that is described by a vector of 197 numbers, and so it's a more complex full body character. And then the action space is basically a set of 36. In this case, it'll be controlled with basically PD target angles, but this can also work with torques. And yeah, so you have to produce these set of 36 numbers that controls the actions. And so so if you control a motion without a target reference motion, just with a pure objective, then if you're really lucky, you'll get a fairly good looking motion like this. So I would argue that's already fairly realistic. But if you really wanted to if you have motion capture data that says, look, here's what a real run looks like, please make it look like this, then on the right is the motion capture data, and on the left is the simulation. And so we can imitate new motions, a variety of motions. But one of the problems we ran into was that for certain types of motions, like a backflip, which is shown in motion capture on the right, then it's unable to imitate that on the left. So basically it falls on the ground, and then it's struggling to continue to imitate the backflip, but while lying on the ground. And so it's basically stuck in this local minima during the learning process. So to fix this, one of the things you can do is as soon as it falls down, you actually stop the simulation, and so that it cannot gain further rewards from trying to imitate the backflip while lying on the ground, right? Because it can still try and imitate the approximate poses of the backflip, and it'll get some partial marks, if you will, for moving its joints in the right action while lying on the ground, but that's not what we want. So if you do what's called early termination, then you fall into a different local minima. So here you'll see on the left, it's basically pretending to do a backflip, but except it doesn't do the backflip, and it goes directly to the landing and says, okay, it basically says, I hope you blinked, and that because it still kind of looks like the backflip overall on the right. So to fix this, we're using something called reference state initialization, which is where in the, I don't know if you can see on the top right here, you really want to initiate your simulations at various points along the backflip, so that it really learns how to do all points along the backflip, all stages of the backflip, and it eventually learns how to connect all these together. And so yeah, so if you put these together, then we can successfully do a backflip, and a variety of other really dynamic motions. We can also condition the policy on a terrain map here. So here, like it doesn't, here it just happens to follow this path, because the only way for it to successfully continue imitating the motion capture data is to follow along this path, right? So it basically always wants to walk straight, but it can't, because it learns that it will fall if it steps off the path. And so so in this case, it can see the path in some crude fashion, but the reason it wants to follow the path is because otherwise it would fall, and therefore it would do poorly at imitating the motion capture data. But this is really fun. The fact that we can already come up with kind of smarter versions of these policies. And so here it can see this green line basically shows. It can see the upcoming gaps, and it needs to avoid these upcoming gaps in order to keep on imitating the motion capture data. So by the way, I just wanted to show what some of these results look like when properly rendered. And so this is from some earlier physics-based work that we did with Libin Liu. And so this is what these physics-based motions look like when properly rendered in something like Unreal Engine. And so I think this is what the community needs to do to convince, to do a better job of convincing the larger animation community that look, we can really do interesting character motion in real time, because the simulation is actually fairly cheap to do, and computing the control once the learning is completed, then running these policies is trivial in real time. Okay, so it just more to convince more convincing of the animation community. This is we applied this to this is actually this is imitating a keyframed motion cycle for a lion. So it's basically hand keyframe. So who knows if it's truly physics based or not, but it turns it into a physics based motion you're seeing here. So this is from the learn policy. And then to make this look good, you take exactly that motion, and we collaborated with Ziva Dynamics, a company in Vancouver that does finite element based muscle simulation. And so once we combined efforts to render exactly the same motions you saw before, but now on this much more sophisticated model, then you get something that looks like this. And so hopefully. Yeah, so this is fun, because now you can get this super realistic lion, and if we could do all the finite element skinning stuff in real time, well, then we have a kind of a real time lion that we can push around, and becomes quite interactive, and starting to get to where I think we always wanted to be. For the past 40 years, I've always wanted to create intelligent characters that can respond to their world. Yeah, and so one last thing you can do is we can build hierarchical structures on top of this, and this is also where there still needs to be a lot more work done on this. So in terms of adding hierarchy and being able to use reinforcement learning or other methods, planning methods to that sit on top of these low-level controllers that we're learning. So LLC here stands for low-level controller, and so this corresponds to this early walking example that I showed you, where it plans to the goal of the low-level controller is to imitate the mocap data and to also hit these 2 target footsteps. And so the high-level controller will actually just generate these dynamically these 2 footstep locations, and so it can basically use this to steer the character. And so now, given a map of the terrain or some other task-related goals, it can learn to generate and guide the motion. And so that could also be solved using reinforcement learning. And so here, what we're seeing is like a simple example of soccer dribbling. So here, the reward, it gets a reward for the character being close to the ball, and also for the ball being close to this target location. And so here, whenever it always walks to the ball, walks around behind the ball, and then starts kicking towards towards the goal. But remember, it doesn't really know that the ball is, the low-level policy doesn't know that the ball is there. The low-level policy is just trying to hit these 2 target footsteps. And then you can do crazy things. You can replace the ball by a box and see how well the policy can generalize with that, and and also switching between different low-level controllers. All right. So a really fun thing is to see whether some of these methods might actually generate to real robots. And so this isn't this isn't directly animation per se, because it's a real robot, but it really represents the impact of this motion imitation style work, which has its origins in animation. So this comes from the animation community, and being applied to real robots. And so so this is a collaboration we did with a company called Agility Robotics and Oregon State University. And so this is a paper from about 2 years ago, or 2.5 years ago, is 3 years ago is when the work was done. So here, again, the task will be the same. The robot's just trying to imitate a single walk cycle that we give it, and then we can also come up with different versions of that walk cycle. So where we have it walk at different speeds, and its goal is to be able to imitate that. And of course, a basic question is, well, okay, how well will this work on the real robots? And so these are actually some of our first learned controllers for this in simulation. And so here it's doing some blind walking over different terrain. This is, and Agility Robotics and Oregon State provided us with a detailed, fairly accurate simulator for this. And so here we are in this is the Oregon State lab. And so when we actually tried to work this is literally one of the first tests of running this in the real robot. And here's what it looks like. It's, oh, sorry, let me move to the right part of the video. Okay, so this is literally one of the first tests. And okay, so as you can see, not very successful. And you'll see him set up the robot again and again, and it has real troubles. So yeah, so the first things out of the box did not work, and so we had to figure out what the issues were, and I'll get back to describing that in just a second. But this is it's also interesting to think about this for animatronics and other kinds of robots, because at some point the folks in robotics, they want to create interesting motions, right? If you see the latest videos from Boston Dynamics, they're all about dancing and doing other interesting motions, and in many ways, that's what we do in the animation community. So, all right, so we did eventually figure out what some of the issues were, and so these are actually this is a deep reinforcement learning based policy, learned purely in simulation and just then run on the real robot. And so here's this robot walking reliably on a treadmill, and you notice it's actually stepping off to the side of the treadmill and still being robust. We can have it learn to walk forwards, backwards at different speeds. We can have it learn to walk sideways. And so yeah, so this is neat. I should mention that the reference motion here, it doesn't need to be a very accurate physics-based model at all. In fact, the reference motion it's really more like a crude motion sketch that says, look, I want the legs to move roughly to the side, or I want the velocity of the body to move sideways. And so the reference motion itself does not have to be physics-based. That's important to remember. And so that's nice, because it gives you as an artist a lot of leeway in just kind of creating, you know, motions where you can say, make the stepping motion look more like this. So here's another style where we throw in a term to minimize the angular velocities everywhere and accelerations. So we're just trying to create a very smooth motion. Here to make it more robust, we add some reward to lift the feet higher. So it's doing robustly there. And yeah, here's just a sign of how robust the motion is. So we're giving these, again, the robot is walking blind, and it's just being commanded to walk at a certain speed. And yeah, various perturbation tests. And so you know, in some ways, the exciting thing about this is you know, you could know nothing. You could really not know that much about, you know, the detailed mechanics of foot placement and control. And yeah, you know, you can run this in well, you know, it still takes a lot of expertise to set up this procedure, but in the end, the reinforcement learning procedure, it is a bit of a black box procedure, right? Okay. So I did say I would get back around to what the difference was between simulation and reality for Cassie, and so to make this work. And so just a few things. Yeah, you do need to have a well-calibrated dynamics model, and it turned out to be important to in training. So in simulation during training, we have access to the ground truth state of the real position and velocities of the robot, but that actually turns, and so you'd think that would be the best thing to give to your control policy, to give it access to the real state. But if you don't have access to that real state when you're actually doing it on the real robot, then that means it's a bad thing to give your policy access to the ground truth state. And so it's better to actually use the same state estimator that's run on the real robot, use a copy of that to also train on, to use during training. So that was one of the key things. And we needed to calibrate the delay for there's always some delay. And so you need to have a model of that. That needs to be the same in simulation and reality. And yeah, and so together with that, and yeah, and then you can get reasonable results. Another thing we had to do was to minimize accelerations of the body, so that a lot of the first early motions that they tended to produce a small shaking motion, which you could hardly see it in the simulation, but when you run it on the real robot, you hear the real robot rattling around a lot. Then suddenly you realize, wow, okay, this is, you know, it's important to create a much smoother motion and to reward that. So just to show you how exciting this is, and that people that the same, largely the same similar team at Agility Robotics in Oregon State, they continue to work on this. And so this is actually a recent work where the robot here it's actually walking completely blind up and down these stairs. Okay, so the robot cannot see the stairs. It's just being commanded to walk at a certain velocity, but it's been trained during training. It's basically seeing similar environments of stairs that it needs to walk up and down. So it knows it might expect a stair up or a stair down at any point in time. And so amazingly enough, if you train on these blind walking tasks up and down stairs in simulation, this actually transfers onto the real robot. And so this is I'm not sure if you or I could walk up and down stairs like this blindly. I suspect we could, but once in a while we would probably sprain our ankles, and so then maybe the robot doesn't have to worry about that. But so this is really exciting to be able to see these kinds of capabilities kind of emerge from these reinforcement learning processes. Okay, so you can also do this. This was a paper led by Xubin Peng, former, who actually was also behind the Deep Loco and Deep Mimic work. And so he also with colleagues, applied it to be able to take motion capture data from real dogs, and imitating that in simulation. So that's what you're seeing on the left, and then further imitating that with a real in this case, this is a Lycago quadruped. And so here we're seeing a Lycago quadruped being trained to do robust turns and backwards walks, and so really being trained to imitate the motions of a real dog. And so and this motion imitation framework can really take you quite far. So now what you've seen previously is generally where we're imitating just a single motion capture clip, but you can also imitate more arbitrary motion sequences. And so the really all you need is you need a short window of the future motion so the policy, if the policy has a short snapshot of the upcoming motion, so say maybe 1 second into the future, then you can build a really good tracking controller that can actually track, instead of just tracking one motion capture clip, it can really track a variety of different motions. And so I'll show that here. So this is work from Jihee Lee's group at Seoul National University. And so here's these blue characters represent the upcoming window of motion, and then the gray is the actual simulation. And so now you can train a reinforcement learning policy that doesn't just memorize how to follow, in some sense, how to follow a single clip, but do a single motion, but really to be able to do motions that can dynamically change on the fly. And so that kind of makes sense, because when you or I walk, then you can imagine that you're always have an intended motion 1 second into the future that you're planning to follow, and then you learn how to achieve that goal, basically. So maybe as one of the last pieces of work that I'll present is stepping stone locomotion. So we've seen lots of work on using motion capture data, and particularly when imitating highly dynamic motions on flat ground. So here we're going to change both of these assumptions. So we're not going to, there will be no motion capture data here. So these will just be kind of pure learning objectives of minimizing energy and achieving, and not falling down. And that's point number one. And point number two is that, we're going to remove the flat ground assumption. So these will be, we're looking to do really difficult steps. And so this is our inspiration. There's a parkour company in the UK called Storer Parkour. I highly recommend watching their videos. They produce all these fantastic, so the question is, what can we do to have our characters be able to achieve these similar kinds of skills? So these are some details on the reward function. I won't spend much time on this, in the interest of time. But the policy is learning to directly produce joint torques, so 21 internal joint torques, and it's being rewarded basically to make forward progress, not use too much energy, maintain an upright posture, try to be the policy in general should be symmetric, and it's trying to stay away from the joint limits. So some fairly straightforward things. And so so with this in place, you can really do a variety of interesting motions. But the key thing here is we do need to use a curriculum. And so the goal of this curriculum will be to start with kind of the easy steps, and then gradually learn how to do more challenging steps. And so I'm going to skip the actual details here, but so this gives, again, no motion capture data here. This is just trained on these pure objectives, and so we can walk up these really steep steps, down steep steps, and up spiral steps, down spiral steps. Also apply, you can apply it to different types of models. So this is the Cassie robot model. And so it can also walk across continuous terrain. So internally, it's imagining the continuous terrain as being a sequence of steps, but the simulation sees the continuous terrain as well as these steps. And so this is, yeah, so we can finally do, you know, really challenging steps, and you can change it to a slight jog, etc. We can also have the character stop and start. So this is great, you know. So we have this procedure that creates, you know, this reinforcement learning policy. It has a lot of smarts baked into it. So that's exciting. It does actually make use of its arms to maintain balance. So here we've actually turned off the control of the arms, and you'll see that it falls. And so this is just evidence that the reinforcement learning policy, it's actually making use of the arms to maintain balance during these steps. Okay, so have time for maybe one more motion that I can show. This is to do to learn how to do the high jump. And so the high jump, it has these really multimodal different strategies exist for doing the high jump. Maybe the most well known is that of doing the Fosbury flop. And so the basic question is, can we discover motions such as the Fosbury flop? And so the answer is yes. So there's only one motion capture clip being used here, and that's just to help with learning the run up to the bar. But everything else is optimized, comes from an optimization procedure. And so it doesn't, it's not aware of how to do a Fosbury flop, but using trial and error exploration, it's actually, we can actually come up with a procedure that quote unquote discovers these different strategies for going over the bar. And so we're really excited by this. So by the way, the policies that are learned are still stochastic in nature. Like at the end of training, it's still applying this noise, and so it's still effectively self-perturbing itself. So it makes it over the bar, you know, a good fraction of the time, but some of the time it doesn't make it over. So for the final policy that you actually deploy, you would turn that noise off. So because that noise it's useful during training. And to produce a really robust high jump, but eventually you would turn that noise off. Yeah, and so I'll, you know, in the interest of time, I won't go into all the details, but there is a curriculum involved here. So anytime that you've decided on a particular what's called a takeoff state, then there is a curriculum on the bar height. So you first learn how to jump over very low bars, and then over time we move the bar up. And as that bar moves up, then that's when you get a strategy like the Fosbury flop, which can emerge. And so that's really exciting. Just to and we compare it to motion capture data in the paper, etc. And so I will refer you to that for further details. So just to give you one snapshot of a current project. So we're working on learning how to get up. And so you'll see here, this is far from a fine-tuned result. So on the left is actually typically what you might get out of the box from the OpenAI gym. So if the character falls, you want it to get up. But you'll see this motion is basically, this character is far too strong. So when it jumps up in the air, it actually goes flying into the air because it's so strong and powerful. So that's an example of the kinds of bad, unrealistic motion that we actually want to avoid. And so the question is how can we, you know, what does it take to use the same reinforcement learning ideas, but to achieve more realistic motions? So one thing we're working on is to make the motion as weak as possible. And so here we're performing some kind of a curriculum where the torque limits become smaller and smaller, and so the character is becoming weaker and weaker. And so here this is already a much more realistic getting up motion. And then the other thing we're doing is we're making the motion slower and slower. And so here this motion is in some sense both weak and slow. and so it wants to get up slowly. And so yeah, so interested in these kinds of strategies. So here's some more examples of the types of motions that we get, even with these weak and slow motions. So one of the challenges of reinforcement learning is of course, yes, sometimes a lot of the time you will not get the results that you want or that you expect, and then the question is how are you going to debug it? Because it's difficult to distinguish between, you don't know if the system is actually capable of the type of motion you want, or maybe it is capable and you're just not finding it with your current framing of the reinforcement learning problem. And now, so these are just all examples of the different kinds of in-between results for this stand-up task, and I'm just showing you kind of the, showing you for a typical project where we're at before we're at this point where we have fantastic results that we like to show, but I think it's important to show these kinds of intermediate results as well. So yeah, so in the interest of not going over in time, I'd like to acknowledge the work of the many collaborators and students who really made all this work possible, and leave some time for questions. And so let me just wrap up with some quick conclusions. So deep reinforcement learning, I would argue it really is a game changer for kind of this full body animation tasks that we want to solve, and also robotics as we saw. It comes with a large set of caveats. So there's a lot of benchmark problems where you don't have to design the task, but if you want to solve a particular task that you're interested in, then that means that there is a lot of non-trivial setup and debugging that you need to tackle, and including you might need to design your own learning curricula. And so this particular idea of curricula is something that I think is largely missing from current approaches, and it's a very powerful idea. It's also slow to compute. So if each time you make a change to your rewards, you have to wait. You have to wait, anywhere between 2 hours and a day to get new results. That makes for a slow development and debugging cycle. But yeah, so overall, there's still a ton of interesting problems that need to be solved. So primarily that of scalability. So humans and animals, we have so many different skills and tasks that we can do in so many different environments. So how do we do that? And then as our policies get more sophisticated, we need better, we need good ways of sensing the environment and knowing where we should focus our attention, where our policy should focus attention in these more complex 3D environments. So to move in these 3D environments, we need to start building notions of attention as well. Yeah, how can we develop universal controllers? So a single controller that can do that can control a human body of different proportions, doing different skills in different environments. Is that possible? And how do we introduce more artist directable motion back into the how do we introduce artist control back into the loop? And lastly, how might we unify animation, robotics, and biomechanics? And so reinforcement learning is a really nice platform for doing that. So let me stop there, and let me thank the organizers again for inviting me. And yeah, if there's any questions or discussion, I'd love to have that. Thanks.
Okay, thank you very much for the wonderful work presentation. And just I want to add, currently Michael van de Ven, he currently serves as the Deputy Director of KAIDA, which is the UBC's main AI organization. And I mentioned many of his students related to the company. Something if I mention a little bit more details, his students and postdocs, they founded or co-founded companies, including Locomotion, VGC Software, Element AI, and Waveley. And then it seems some of them are also leading. They have leading roles in Tesla as a director of AI, and then autopilot version and team motion.
I just work with many students who are smarter than I am, so that's the key.
Yeah. So there are some questions, but actually I really want to ask, so I'll go first.
Sure. Yeah.
Yeah. So for me, I got to know about the reinforcement learning a little bit more like from the AlphaGo. Yeah, because the AlphaGo and then AlphaZero, it was a very like the it gave a very big impact to the world. Yeah, so like the people started to think, oh, now the human is really inferior to the AI. Yeah. But at the time, the AlphaGo and then AlphaZero, they had very different idea. So AlphaGo learned from human examples, how they play Go game, but AlphaZero didn't learn from the examples, but they just got trained by themselves, maybe by playing, without just with the rule and then the goal. So it was, but they didn't learn any examples from human plays. But I learned, I heard the AlphaZero, which learned how to play the Go game. They play more similar to human playing. Yeah. So now when you use your reinforcement learning, is your reward more like a human example is a reward, or do you use a lot of human examples to build your reinforcement learning, or is it more like a really rule, like you need to not to fall down, but you have to reach over there?
Oh, okay. Yeah. So that's a great question. You know, we've all been inspired by AlphaGo and AlphaZero. I'll just make one comment that in reinforcement learning, working with discrete actions. So where you know in AlphaGo or AlphaZero, you need to place a particular piece in one location, or in the Atari games they have discrete actions, and so that really uses. That really enables, in some sense, those problems with discrete actions are quote unquote easier than or different. They have a different flavor than problems with continuous actions, and they need to use so they need to use slightly different algorithms. So that's just a comment I wanted to make there. I guess the major comment I wanted to make there was that it doesn't necessarily make sense to use all the techniques from AlphaGo or AlphaZero and apply them to character animation, because some of the techniques are really tailored towards discrete actions, whereas working with continuous actions, it's a little bit of a different game. That's one thing. As thinking about using data, using mocap data or not, we've actually been on both sides of that fence. And so with the Deep Loco and Deep Mimic, we're using motion capture data, and then with the stepping stone work, we're not using mocap data, and the high jump work, we're also not using motion capture data. And so with the exception of the run up. And so, I think it's interesting to explore both. And the real question is, we don't really know, as you mentioned, it's difficult to know what is the objective function for a human motion that we're really optimizing. And in fact, that's where arguably we should be using more biomechanical models if we actually wish to more accurately model those human objectives. But we've been surprised how well you can do even without a biomechanical model. So with the stepping stone work, we've it does take some effort. Like there are maybe, I think there's five terms probably in the objective function there, and so we do have to add something that says, oh, by the way, try to keep your body vertical upright, because we think that looks more natural. And so there's a few basic terms like that, but surprisingly, it wasn't too hard in that case. But yeah, in the long run, I think we'll always need both basically, or yeah, in the short run, it's useful to use whatever information you have available. But for the stepping stone data, it's difficult to find good motion capture data of all stepping stone scenarios, right? So that's one of the reasons why we went with the pure objective.
But like walking is there, but like for example, high bar, the jumping, that's
all learned. Yeah, that's learned. Yeah. So there's no motion. There are no high jumps in our. There's no high jumps data at all in the high jumping work. So that's actually the exciting thing is that it does discover that Fosbury flop along with some of the other solution modes. It's still not quite as good as what like some of the other modes are still not completely natural because like you can also jump over a high bar using a large scissor kick, and so we don't fully get that scissor kick because we don't optimize for the landing for landing on your feet. If you want to get a nice scissor kick over the bar, then you should also optimize for landing on your feet, and then I do think you could get something that looked very much like kind of a classic scissor kick jump over the high bar. But yeah.
So thank you very much for the very nice answer. So now let's go for questions. There are several questions. I think I took a question a little bit. Right, so okay, so first question from Chi Zhu. Could the physics simulation run on GPU? It may cost one day to mimic a single motion. Any solution to accelerate training?
Yes, yeah. And in fact, so absolutely, they can run on the GPU. So NVIDIA is working. Well, so they've always run on the GPU for kind of blowing brick walls apart and things like that. But now using their Isaac simulator, they're running the multi-rigid body articulated body simulation. They're doing simulating like 1,000 robots or characters in parallel on the GPU. Yeah, absolutely. So that's and that will speed up training. So that's exactly a direction that people are going in, and that in some ways that connects with Richard Sutton, kind of one of the pioneer of reinforcement learning. He has this thing he calls the bitter lesson, and his bitter lesson is that basically more compute almost always wins. So basically, yeah. So suddenly, if you can use GPU-based simulation for everything, then a lot of this learning will go even faster. And so yeah. So have a look at the NVIDIA simulator called Isaac. And so that's something that I think you still have to sign up for it, but yeah. But it's free to use, and yeah, and that will change things as well. Yep.
And usually, how long do you do for training?
Yeah. So we're actually still. Yep. So we actually do all of our simulations still on the CPU, and just use the GPU for the policy updates and the neural network learning. But so for something like the stepping stone work, like once you have it all set up, I think it learns in I don't know 6 to 12 hours or something, like I did just on a 16-core desktop or something. But so in some sense that's not the issue. So you might say, okay, that's kind of reasonable. But you know, the harder part is still the debug cycle, right? Because now it's fine if you compute your final results in 6 hours, but if your debug cycle is 6 hours, then that's not so good, right? And so that's where you really want you really want to. That's where it would be fantastic if you could take that from 6 hours down to 10 minutes or something. And yeah, so and I think that is where we're going. Yeah, so for a lot of the work on quadruped robots, there's that's where NVIDIA and another simulator called RISIM, that's where they're kind of doing a lot of their benchmarking for this, and they are able to learn controllers like in 10 or 15 minutes. So yeah, so that's coming.
Yeah. Okay, so there is a question from Lia Zhu. Thank you very much. The research are amazing. Just wondering, is there research using the learning of a character's weight to control their motions? For example, would the asking agent to learn keeping stable over their weight center might help them to perform better in the motions.
Oh, okay, yeah. So
it's more like the center of mass learning stuff balancing.
Right, yeah. Okay, that isn't it. Yeah. So so currently, like none of these characters, none of these controllers knows anything about the center of mass, and so in some sense that was kind of the previous approach in robotics was always to build a model where you provided a simplified model that consisted of the center of mass and the location of the feet, and so and that makes control and learning faster because the model is really simple, and you're providing it so you're providing it with some key features, right? Because the position of your center of mass is obviously important. But so the interesting, so in some sense, reinforcement learning throws all of that out. It says, no, we don't need any of that. We'll just learn we'll just learn how to maintain balance without being told these quantities. So and so that's both, you could argue that's both good and bad. So it's bad in the sense that if we have knowledge of something like the center of mass, then surely that would help speed the learning. And so we have used that in some work. So in some work with Professor Tae-Soo Kwon, we've done some work where we do train on these kind of simplified models first, and that will learn faster, and then you can try to upmap that to a full physical model. But in general, something like the center of mass, it really is an imaginary quantity. So like in some sense, it doesn't exist, right there. So the center of mass is just this artificial quantity that we've dreamt up to make modeling simpler. And so that in some sense, that's one of the strange things about this kind of more black box approach is we throw some of that stuff out. But where it does come into play is if at some point you really want the learning to be very fast, then you want to do something more like trajectory optimization and less like reinforcement learning. And so in trajectory optimization, you're trying to solve for a single trajectory rather than a full policy, and there the center of mass model and other simplified models are incredibly useful. And the nice thing there is you don't have to wait hours. You can instantly optimize for that. And so Boston Dynamics uses a lot of trajectory optimization, smart efficient trajectory optimization to online to make small adaptations. And so they're not using these pre-computed reinforcement learning policies, although they've done some experimentation with that. But so that's where to make these models work really fast, then that's where the simplified models definitely still help.
But the Boston Dynamics did with the real robot, so the weight parameter is really important to do the real simulation. But,
yeah. Oh, okay. Yeah. Oh, right. Okay. Okay. So yeah. That's yeah. Maybe I misinterpreted the question there. There's still the notion of, okay, if you, of how much does your character actually weigh, and how do you make your controller robust to that? Yeah. So that is absolutely important. There has been some work on. There's been some papers by Jihee Lee's group at Seoul National University on learning a controller where as one of the inputs you give it the mass of the character and the proportions of the character, and so that starts to go in the direction of a universal controller that can control characters of different proportions and different masses, etc. So yeah, so people have begun to look at that, of building a single controller that can also can control characters of different masses and different proportions. Yeah.
Okay, so next question. Okay, so I didn't read the Jiaju's next question. Aside from robot and game, what are the potential applicable areas for future character behavior simulation?
Oh, okay. Yeah. Okay. Right. Yeah. I'm cautiously optimistic for using for this kind of animation in games, and also for design. So at some point, yeah, for ergonomic design for games. Honestly, like I think once we have really good human models that use both physics and can do and we know how to compute, intelligent control, then we can use them for all kinds of things, right? So in some sense, yeah, it's yeah, we can do lots of things with human models. But these will not solve all problems right away, because if you're working on a particular shot for a film and you want your character to do something very specific, then at some point your best way to tackle that is may still be to have an artist actually design the motion, etc. And another issue with games and visual effects is that in many cases you don't want a physically based motion, and so in the sense that you might want your character to be able to do something that's impossible, and so that needs some external assist, right? So if you want a Superman or something that performs a superhuman motion, then yeah, that's actually something that myself and others are also interested in. So how do we take some of these reinforcement learning ideas and also still be able to apply them in settings where it's okay if the final motion is not 100% physically realistic, but we can still you want to have all the realism of the physics from the contacts, and it should be mostly realistic, but then maybe you still want your character to be able to turn very quickly or jump a tall building. And so I think that's a really interesting direction that hasn't seen much work. So yeah.
Possibly if it's a very physically correct motion, if we can be like walking, we can use those things for park design or some kind of a trekking design on the mountains.
Yeah. I mean, actually, like hiking up a mountain path, was kind of one of the inspirations for the stepping stone work. Is like, okay, so we got tired of working with just walking on flat terrain. So how do we have something that can hike? And but yeah, I actually think there's a really interesting work to be done with climbing and really working in more challenging environments. And this is also where a lot of quadruped robot work will probably go, because eventually you want to send quadruped robots where you don't want to send people, basically. And but yeah, so those are still hard problems. Like how do you really deal with fairly arbitrary environments, and that's where, you know, real people and animals are still so much better than our best simulated characters and our best robots. So we have plenty of work left. There's always plenty of work left to be done.
Yeah, sure. Yeah. Okay, so are there some more questions?
Yeah, if you, I could ask a question.
Yeah, sure.
So I was wondering, like, with respect to this adaptation to like difficult terrains or like robustness, how do you feel that would be? Would it be harder or simpler to optimize for dancing, where you need to kind of match the rhythm, match the footsteps, and so on?
Yeah. Dancing is a super interesting category of motion, and I'd really like to see. Yeah, I hope we'll see more work on that kind of problem in the future. I guess they focus on different. In some sense, the variable terrain stuff it's almost easier than the dancing problem, right? Because whether a dance is correct or good or not is more in the eye of the beholder. And so normally whereas to generate a character that can go on different terrains, then, you know, it's easy to come up with a procedural generator that just progressively generates new terrains and more difficult terrains, and that's kind of what we did with the stepping stone work, and I think what other people do as well. But for the dancing work, there I think, you know, one of the best tools is basically coming up with discriminators and using like a GAN style approach for to determine whether a given motion you're seeing, whether it came from the policy you learned or whether it came from a real dancer, right? Because then ideally, if your network can't tell the difference, then that means that a real person can't tell the difference either, right? And so that GAN style generator framework is what's used in images, right? Like how do you define what the image is, what a realistic image is of a face? Well, it's difficult to define that, and so therefore you just learn a discriminator that also tries to do the job of a human, saying, okay, that's fake or that's real. And so yeah, so the question is, how well can these GAN style discriminator based approaches work for motions? And and there's some work at SIGGRAPH this year from Zhubin Peng again on using discriminators. But I think there's a lot more to be done there as well, and I think that would be the approach you might want to take for dancing, maybe.
Great, thanks.
So just now you mentioned about the GAN system. So GAN has been really powerful, and then reinforcement learning is also very powerful. How do you compare these two? Do you think reinforcement in learning is good for something, and then like a GAN, well, nowadays also there is some kind of a graphic CNN, which is maybe people do with the animation a lot. So how do you compare the reinforcement in learning and then GAN in which area of animation?
Yeah. I mean, well, okay. So yeah.
Which one is stronger for which one, and then
right. Yeah. So in one way all of the work that I presented here is you know, it uses physics 100%. But an alternative way is to just generate motion without using physics. Just from you know, there's lots of motion capture data out there now. You know, why bother with physics? Because when I'm looking at an animation, I can judge whether I can use, you know, when I look at it, I can see whether it's physically realistic or not, and I don't need to be running like a full dynamic simulation in my head. So I do think that is a valid alternative approach, is to say like, don't even bother simulating physics, just collect lots of motion capture data and just model, and eventually from vision as well. So as computer vision gets better and better at doing virtual motion capture data, then eventually we can use almost every video from YouTube as a motion capture source, and perhaps and therefore we have so much real motion data that we don't need to simulate physics. We can just generate motions that are realistic without truly being able to, without truly needing to generate the motion by using physics. But so far, like for a lot of the animation-based work, you still need to do special things to get rid of foot slip, etc. And so I think that there are some constraints like foot slip and other things that are just that ideally like a GAN discriminator should be able to say, aha, I see the feet slipping, so that's a fake motion, and therefore it should be able to improve some automatically generative policy, again with no physics, that just generates new motions that look realistic. Yeah, so I think that approach will proceed in parallel, right? Because so far, the real uses of animation systems that actually use full body character physics, it's very small, right? Like because games have not adopted this yet. Visual effects, games and visual effects, they've kind of adopted it for the for when you fall, but aside from that, they want to control every aspect, and they can collect lots of motion capture data. So yeah, I think we'll see those approaches continue in parallel.
Yeah, data is available a lot in the world. Yeah.
Yeah, and I think there's a lot more to be done there as well. But the physics is nice because actually one counterintuitive thing is that a lot of physics-based generated data, it's like doing something like Deep Mimic is actually a good way to clean up motion capture data, because motion capture data, people treat that as the ground truth gold standard, but as anyone who's actually done motion capture data, like it needs cleanup, and so the feet slip, and it's not nearly as nice as you think it is, and so in some cases there's an argument to be made that the physics-based simulated data is better than motion capture data, because you get the crisp contacts, etc., and you get these high frequency components that are missing from the motion capture data. But yeah.
Okay, yeah, thank you very much. So if there is no more question, maybe we appreciate your older presentation and nice response to our questions. And then
thank you very much. Yeah, this is really fun to give the talk and all the great questions. Yeah, really fun.
Yeah, okay, thank you very much. And then thank you everybody for attending this keynote session. Yeah, thank you. And then bye-bye.
Cheers, thank you, bye-bye.
Thanks, goodbye, Michael.